Hello, students. I had a few questions come up in the homework, so I'm going to pop into GeoGebra. This is about Module H, the module with the GeoGebra digital activities. Let's take a look and see. Question is, hint on constructing 8B. Okay, so let's see here. Question 8B is repeat the process using 4 circles. So this is drawing a rectangle that has 2 circles included in it. Now, I would recommend, to be perfectly honest, I guess my hint would be to build the circles and then build the rectangle. So for example, if I build a segment here and I build a circle with a particular center, let's see here. Let me get my midpoint down. And so if I click a midpoint here, I could build a circle with this center like so. Right? I mean, that's not a huge thing. And I could actually create another circle like this, and let me make a line out of this one so we can just keep going. And the goal is to kind of remember, I want this kind of diameter in play. And so I kind of need points. I need to know where the points of the circle will need to be. So what I'm going to do is I'm going to create this other one and then hide that second circle. Now take a look at what I have. I have a point here that's kind of the center for the first circle. And then I have this new point, which I know is the same distance away. And I could use the circle one more time, just go this direction. Now I guarantee they're exactly at the correct distance. They're touching exactly once. I make another point. Then I build another circle here, which I know I'm not going to use, but all I'm doing is building this additional point to the outside. And then the circle I actually want is the one all the way out here. So I'll build 3. I'll hide this one, and you can come back, and there we go. If you want, you can also then hide the line, because we don't really need it. And I could even hide the other little piece right there. And again, if I'm just looking at circles, I don't really need the centers. I'll leave them there just temporarily. But now I do want to build a rectangle that goes around the outside of the box. And that's where, if you have the line, you can build perpendicular to it that goes through a particular point. And you can build a perpendicular that goes through it way over here. And the reason why we can even build a point of intersection on the right, and then once again do a perpendicular line that goes through over here. So what I've got is I've kind of got the verticals on the edges. This one that I chose in the middle may seem a little bit out of place, but I'm using it to find a single point and then create a perpendicular that goes through this point, if that makes sense. So what I'm doing is I'm making that, I know I want it to touch exactly once, and so I'll make that touch exactly once, followed by creating a point down here at the bottom, and then repeating with a perpendicular line so it touches here. And then probably, since I want to do a polygon here, I would make some points and say there's a point, there's a point, there's a point, and there's a point. So I don't have to try to break it into segments. It can be kind of quick and easy this way. And then I will just hide all of the lines that I made along the way. I'll just click to hide those and make sure they disappear. And then what else do I want to hide? I think I'm going to hide point I and point H just because they were kind of in the way. Make your polygon with the outer 4 points that you just built, guaranteed to touch exactly once. And that's how you can do it for 3 circles, very similar for 4 or 5 or 6 or however many other circles you need. And there you go. That's that. So there's the hint on how to build that one. And let me see, let me get the homework open up over here. So that's 8B to repeat with 4 circles, okay? And let's take a look here. Student says number 1, so let's see here. Figuring out percentages by 7a, the non-circle area would be the area of the square minus the area of the circle times that by 100. So let's take a look at the question for 7. Find the percentage of area in the square not covered by this circular region. You could set it up in a couple different ways. Let me jump over here and share just kind of from this image here. And so we're looking at 7, part A. And so what I guess I'm looking at here, let me add my annotation window. There we go. And so, oh, I gotta be careful. It's not gonna let me do that because of the way my tool works. Okay, new share. Here we go. There we go. Oops. All right, so for this one, I think the biggest piece is when you're looking for a percentage that's not covered or that is covered by something, there's many ways to do it. I always prefer the way that does not involve a ton of work. Let me give you an example here. So if I gave a square, right, and I gave like a little piece that's right here, and I know the area of the big piece, and I know the area of the small, what I can do is I want to find the percentage of the area that's in the big square that's not covered by this. I'm trying to find, in a sense, this red region out here. Now you could go through and do big minus small. Now that would give you the area that's remaining, right? But it's the percentage of the area in the big square divided by big. So you could go do all that calculation. What I look at is if I simplify this, big divides into both and you get 1 minus small over big. This is basically saying if you just took what part is the small part of the big, let's just say that maybe it's 20%, then 1 minus that would give you 80%, and that would be what percentage is outside of that. So if you've got a square with a circle inside, a square with a triangle inside, whatever it is, whatever shape it is, right? Then you could say, well, I know the area of the circle is here, but there's some stuff that's missing. So the big one in this case is the square. So the square goes on the bottom, and you would just say, put the circle over the square, and it's not going to use up 100%, right? So let's just say, I don't know, maybe it uses up 70%. The circle looks like it takes up quite a bit of it here, but let's just say it's 70%. 1 minus 70% would be 30%, and that would be the percentage of the area not covered by that region. And then you reverse it for the other one because now the circle is the larger piece. So now it's 1 minus square over circle. That's kind of the idea. Okay, let me take a look and see. Oops, let's see here. New share. Okay, what do we have here? We have how to figure out which peg best fits in the hole. Oh, so when you're looking at which peg best fits in the hole, the best fit would be the least amount of wasted space. So I'll leave it at that, okay? That should take care of it from there. If you can waste very little, you're in good shape. And in number 11, the triangles are equal. This is the one with the centroid. That's right. So when you construct this, let me jump back to GeoGebra because this is a centroid. And then you measure the little triangles, if I remember correctly. So let's go ahead and jump back to GeoGebra. GeoGebra.com. Okay, so let's just go up here and we'll just clear it all. And no, discard. Okay, so now I'm going to build myself a triangle, right? And then I need the midpoints of the side lengths. Woo! Cancel. Undo. I may need to draw the segments. I thought the segments were already in there, but maybe not. Let me check. Midpoint or center? Oh, I can select 2 points. Okay, that's what I'll do. So midpoint, I'll just select 2 points. There's the center, select 2 points. There's the center, select 2 points. There's the center, and then draw segments across here and here and here. And I think it says label the point, and it's centroid G. Okay, so they know when you're doing this that you would have a point in the middle, and that point would go in order. So I'm glad they called it G, because they knew what would come next when you label. And then let's see here. Move the actual picture off to the other side. There we go. All right, so it says measure the areas of A, B, G. Okay, so I need a polygon. A, B, G. Got it. Okay. And let's see here, that height. So I need to measure that. Oh, measure the area. So I need to go down here to area. So area, I want to click on this one, ABG 5.1. Okay. And then I have BCG. So again, I'll make, go back up to polygon, and I'll make BCG. Okay. And I can go down and click on area and select the area of that, BCG 5.1. Okay. That's kind of cool. Okay. And lastly, ACG. Okay, so do again, polygon A to C to G and back. Click area, click that. Oops, I did not click area. There we go. And there we go. So area ACG is 5.1. Now, if I click the move icon and I just grab and pull these away, the areas change, but you'll notice the areas of all three of those triangles are identical. No matter where I pull this to, I can make it a really tiny shape. Ooh, I can make it bigger, but they all always seem to be exactly the same. Okay. Phew. So when you're looking at this, you can see now from the program that the areas are exactly the same. But why are the areas exactly the same? And so in order to do that, yeah, I think, well, part of this comes, well, we definitely need some side lengths. So you could pick your side lengths however you choose. But for example, in the triangle, let me move up here. So in this triangle here, which is BCG, you could pick any one of these side lengths to be the base of your triangle. And in the prior activity, one of the activities, you got a chance to see that these lengths, DG compared with CG, those are in a 3-to-1 ratio. And what that means is that, all right, I'd say a 2-to-1 ratio, but there's a cutoff point here. So this length right here would be the same as this length right here, which would be the same as this length right here. So there's three pieces. 2/3 of it is the long piece. 1/3 of it is this shorter piece. Okay. So as I take a look at this triangle, right, I can look and I can say, well, wait a minute. As I look at this triangle, this BCG, whatever it is, has a particular height. And that comes from an altitude making a 90-degree angle. And that height, the area of BCG is CG times H divided by 2. Now, again, I'm not asking you to demonstrate this. Right now, the problem only says make a conjecture. The conjecture you might make is, I think the areas are all the same. And so you would say, okay, that's the same here. But then over in this next triangle, right, you would say, well, wait a minute. The area of BGA, well, I could find this portion of it up here because I know the height of it, and it's 1/3. So I know the height is H, and it's multiplied by 1/3 of DG. All right. So now I have this portion of the triangle is 1/3 of DG, and DG, we already said, sorry, 1/3 of DC, that's what I should say. And this over here, CG, which is the same thing as 2/3 of DC times H and the whole thing divided by 2. And when you simplify that, you'll get DC times H times 2 divided by 3, but then you divide by 2, and the 2's cancel, leaving you DC times H divided by 3. DC times H divided by 3. And over here, this piece right here, this triangle up on top is 1/3 of DC times H, the whole thing divided by 2. And so what you get is that this piece right here, this little chunk, is exactly half of the area of this component right here. This component down here, you repeat the argument down for this bottom one, right? This bottom triangle that you end up with. And you get this kind of fact that, well, wait a minute here. If I look at this length, right, this triangle over here, again, has the exact same area. It's the height of whatever height this is over here. I'll call it H2, this second height multiplied by this base. So like this one up here is DC times H over 3, and this one down here is DC times H2 divided by 3. And then you come down, you say, well, DG, which again is 1/3 of DC, and we get very similar component here. And what's great is that the area of these two triangles, let me change color to maybe purple, of this triangle right here has to be exactly the same as the area of this triangle here. And the reason is that the base along this side is been cut in half. So they have the same base, and these two triangles have the same altitude. So once you're able to say these two are exactly the same area, then this one is half of that one, and this is half of that, which means all three of these big triangles have to have exactly the same area. So that is super cool, at least in my mind, it is. Hope that helps get you going on the right track. If you have other questions, please let me know. I'll see you soon. Off you go.